Alright, so here is the last section. This one's all about electromotive force. This is the end of the end. We're almost done the entire course, so hang in there. This section should be easier than last, so it's okay. You'll do fine. So what are we going to do in this video? Well, we're going to learn about electromotive force, EMF, what is that, and we're going to solve some problems. Let's dive into this. We know batteries are a source of potential difference, or voltage, for a circuit. Now, a battery by itself, when it's not connected to a circuit, there's still a potential difference between the two ends of that battery. You're still having some voltage between them, but you're not actually connecting it to a circuit yet. This voltage, when you're not connected to a circuit, is called electromotive force. Even though it says force, it's actually voltage. Again, back when they were starting things out and they were learning about electricity, they thought there was an electric force that was pushing stuff through a circuit, which wasn't actually true. There is such thing as electric force, but it is not what is working here in a circuit. So electromotive force, even though it says force, is a voltage. As soon as you take that battery and connect it to a circuit, your voltage or potential difference between those terminals actually gets smaller. And the reason for this is inside a battery, you have an internal resistance. So just the mechanics of what's happening inside the battery, there's a resistance inside, not an actual physical resistor, just the way that it works, there is resistance. That's a lot of information. Moving along. Here's the equation for it. So V terminal equals epsilon minus IR, where V term, that's your terminal voltage. It's just what's the total voltage. This epsilon, that's your EMF. Capital I is your current, lowercase r is the internal resistance. Not to be confused with the capital R, which is external resistor. So just be aware of the difference between those. And also note, I times R, that is the internal voltage drop inside your battery. So that is the voltage you lose inside of your battery. Another note, if your battery is not connected to a circuit, no current, so the capital I is 0, your terminal voltage is equal to the EMF, which is the concept that I just showed you. So this equation works with that concept. So here's a diagram of what a EMF looks like in a diagram. So we have that dotted line. That is to signify what your battery is. The terminal voltage is on the outsides of the battery. And notice little r is inside the battery along with the EMF. Capital R is on the outside. So anytime you have that dotted line, you know you're dealing with the EMF. It's pretty straightforward to see that inside of a question. Another note, I know I have lots of notes with this. Your battery goes dead because this internal resistance builds up until the internal voltage drop matches the EMF. Let's do a question. We got a battery with an internal resistance. We want to know the terminal voltage. So use the equation, plug in the numbers we know, find the terminal voltage. Pretty straightforward. I'm not even going to bother explaining that one. Plug in numbers. This question can be a little bit trickier. So what's the voltage drop across the external resistor? So what is V1? I guess we could call that resistor 1. So in this question, we know V equals IR. And there's a little trick with this actually. What we can consider doing in this is say that V, my total voltage, is actually going to be the EMF and pretend like this dotted line doesn't exist. So my resistance is R, little r, plus capital R. You can do this assumption. It's going to make the math a lot easier compared to the other way that I used to teach it. So this is a little trick you can do that'll help you to solve for what your total current is. Because then once you have your total current, you have your external resistor, and you'll be able to solve for what that voltage is. So that's a little trick you can remember. If you have that dotted line, you can pretend like it's not there and just do the whole circuit as one thing. One last side note. Okay, this is the video of side notes, I guess. If you're wanting to charge a battery, what you need to do is you need to provide a larger voltage to the terminals of that battery. If I want to recharge a 9-volt battery, I need to connect up something bigger than 9 volts to force those electrons to go backwards and recharge it. So you have this equation. It's not in your formula sheet. You're not going to see that on a test or anything like that. But just in case, I think in some of the practice problems, this shows up, but I'm not going to put it on a test. But the equation just becomes a plus instead of a minus. That's all you need to know with that. Don't need to know it. Just a side note. there you go. We are done with everything. We're done with the unit. We're done with all the units. We are done with Physics 11. So I hope that you enjoyed the entire course with this. I hope this unit doesn't leave a bad taste in your mouth for Physics 11. Most students hate circuits. I actually find it's one of the most fun because it's more problem solving, but I know I'm different than most people. So we're done. Congratulations, you made it to the end of the course. So here we got Winter Soldier again. This one's a different scene. Take a look, see which physics concepts don't seem to make sense with this one. So with this one, neat fight scene, but there's a lot of small things in here that just don't add up. It's very subtle, but it's these little things of like conservation of momentum and Newton's third law, lots of these things that don't really look great in a fight scene. There's some things in here that just make it look a little bit more cool. So for example, in this part here, so Captain America's running up towards him, he's running super fast, and then there's a collision between them. The conservation of momentum should say, if he runs up that fast, there should be some movement afterwards. The momentum before this collision should equal the momentum afterwards. If he's running up towards him, there has to be some sort of momentum afterwards. And just little things like that. He kicks him back. Okay, so he falls downwards, but with the amount of force that Winter Soldier kicked Captain America, he should be moving backwards more. It's not like Winter Soldier is that much heavier. So same thing with this part here. Winter Soldier throws Captain America, he goes super flying, and then nothing really happens to Bucky. So stuff like that where it's like, in order for Captain America to get tossed that far backwards, there needs to be some momentum going the other direction. Think explosions with collisions. And because Winter Soldier doesn't move that far back, it doesn't actually work out the way that they showed here. The physics behind this, not super realistic, but cool fight scene nonetheless.